Okay, so today we're going to be talking about relative extrema, section 4.2. And so when we're looking at relative extrema, one of the things that we'll be interested in is points that sit higher than their immediate neighbors, like this point right here, or points that sit lower than their immediate neighbors, like this point right here. And we're going to want to describe them. And so we're going to make up some vocabulary that will allow us to talk about them. And so here we have a function f is said to have a relative maximum at x naught if there is an open interval containing x naught on which f of x naught is the largest value. That is, f of x naught is greater than or equal to f of x for all x in the interval. So what you see here is that at this point, at this x value of x1, we can draw a little interval around x1, and every input in this interval will have a corresponding output that is less than the output for this point. Likewise over here, we can draw a little interval here, and every x value in this interval will have a y value that is more than this than the y value for this point. And so that is a relative minimum. And so there's our next definition. Similarly, f is said to have a relative minimum at x naught if there is an open interval containing x naught on which f of x naught is the smallest value. That is, f of x naught is less than or equal to f of x for all x in the interval. If f has either a relative maximum or a relative minimum at x naught, then f is said to have a relative extremum at x naught. So we're going to want to find these points of where we have a relative extremum, and what you can see is that should make sense from the graphs we were making last time, that if you are increasing, and then leveling off, and then decreasing, you can do that in one of two ways. You can do it in a nice, round, smooth way, and in which case then the slope of your tangent line will be horizontal, so the slope of your tangent line will be 0. Or that's happening here and here. Or you could go increasing, and then make a sharp turn. And so when you make the sharp turn, the tangent line is not defined. The slope of the tangent line is not defined, and so your derivative function should be undefined at that input. And so that leaves us to our next definition. A critical point for a function f is a point on the domain of f at which either the graph of f has a horizontal tangent line or f is not differentiable. Points where the derivative is 0 are called stationary points. So we begin with our first exercise, and we're looking to find all the critical points of this function. So to do that, first thing we need to do is we need to figure out what is the derivative. So you should, if you feel comfortable doing what we're supposed to be doing, you should pause the video and do what we're supposed to do, and then play the video and see how your work matches up to mine. But so here, find all the critical points. All we're being asked to do is find the points at where the x coordinates of the points at where your derivative is 0 or undefined. And again, notice that your book uses the phrase critical points, but we're only looking for the x coordinates. So we have our derivative is 3x squared minus 6x minus 24. To find the critical points, we just need to figure out where is this derivative 0. So to do that, we could write this function in factored form, factor out the 3, and we get 3 times x squared minus 2x minus 8. We can continue factoring, and then we get 3 times, it's a trinomial, so we put our two binomials. X squared only comes from x and x. The minus comes from plus and minus. We're looking to multiply together to make 8 and subtract to make 2, 4 and 2, but we want to end up with a negative. So we end up with x plus 2 x minus 4. And so then our critical points are x equals negative 2 and 4. Another strategy that we could use is, rather than factoring and finding the critical points by inspection, since we're looking for the zeros, we can just set the derivative equal to 0. And so we can just replace the derivative with 0. And so we get 0 is equal to 3x squared minus 6x minus 24. And then we go about solving that equation. In this case, since we're dealing with a quadratic equation and we have one side as 0, we could, rather than factor out the 3, we could just divide everything by 3. And that will leave us with 0 is equal to x squared minus 2x minus 8. And then we factors the same way, x minus 4, x plus 2, and then we get that x is equal to 2. X is equal to negative 2 and positive 4. And those are our critical points. Our next concern is to figure out, well, how are we going to find our relative extrema? We know we know what they look like, and so then we have this theorem that tells us, suppose that f is a function defined on an open interval containing the point x naught. If f has a relative extremum at x naught, then x equals x naught is a critical point of f. And that is either f prime of x naught equals 0, or f is not differentiable at x naught. Again, this should be intuitive. If you're going to have a relative extrema, then you needed to have been going up and then leveling off and coming back down, or you were going up and then made a sharp turn. And at either case, then your derivative is 0 or undefined, and so then that gives us the theorem. And so we're just gonna, the theorem is fairly intuitive, and we're just gonna leave it at that. Next, we'll look at some possibilities, some different shapes for graphs. So here at x naught in all of these pictures, we have a relative, we have a critical point. So these are all critical points. In this first one, you're increasing, flattening out, but after you flatten out, you continue to increase. So you do have a critical point because you flattened out. It's a stationary point because you flattened out. It's an inflection point because you can see that the graph on the left is concave down and on the right is concave up, but it's not a relative extremum. Similarly with this one, except in the opposite direction. In this one here, again, you have a critical point, but you're not flattening out. As you approach this point, your tangent line becomes more and more vertical. All your slopes are positive, but they're going off to positive infinity as you get closer to this point. On the other side, all your slopes are positive, but they're going off to positive infinity as you get closer and closer to this point. So this is not a stationary point because the derivative is not 0. It is an inflection point. To the left, it's concave up. To the right, it's concave down. But it's not a relative extremum. The mirror image is happening on the next one. And so here's, for polynomials, here's what you'll see. You have a critical point. The derivative will be 0. And it does change from increasing to decreasing. And so you have a relative maximum. So you could have a cusp. This is a cusp. And so now you're increasing and then decreasing, but your derivative is not 0. So you do have a critical point, but it's not a stationary point, and it is a relative maximum. Over here you have the images with the relative minimums. Okay, so in our last slide, we saw that having a critical point is not enough for to let us know that we have a relative max or a relative min. And so we'd like to figure out how are we going to know that. And so we have a couple theorems to help us with that. Theorem 4.2.3 is the first derivative test. So suppose that f is continuous at a critical point x naught. If f prime of x is greater than 0 on an open interval extending left from x naught and f prime of x is less than 0 on an open interval extending right from x naught, then f has a relative maximum at x naught. If f prime of x is less than 0 on an open interval extending left from x naught, and f prime of x naught on an open interval extending right from x naught, then f has a relative minimum at x naught. If f prime of x has the same sign on an open interval extending from left from x naught as it does on an open interval extending right from x naught, then f has a relative extremum at x naught. That's a mouthful, and our sign charts are going to help us keep track of this in a much more intuitive way. So what we're going to do is we're going to make sign charts for our first derivative. This is called the first derivative test, so you should label your sign charts with the first derivative. You're going to put your critical points on there. Those are the only points where your derivative has a chance of changing from positive to negative, so those are the only numbers that will be on there. Let's go ahead and call that x naught. And what the part A says is if your derivative is if your derivative is positive on an open interval extending from to the left of x naught, and then it's negative, then that meant that you were going up and then coming back down, and so then it should be intuitive that you have a relative max there. Part B says that if you were looking at a critical number at x naught and you were negative on the left and positive on the right of that critical number, then you must have been going down and then up, and so then you were going to have a relative minimum at x naught. And part C says if you don't change signs, then you don't have a relative max or a relative min, and that should be intuitive. Okay, so next we want to find all the relative extrema of the polynomial that we've already found the critical points for. So again, we already found that our critical points were at x equals -4 and at x equals +2. Sorry, no, that was at x equals +4 and x equals -2. Okay, and so then we already saw that our derivative was in factored form 3 times x minus 4 times x plus 2. And as we've done before, we can use this to make a sign chart. The only numbers that go on my sign chart are the critical points, the -2 and the +4. And you can see that when you are using numbers to the left of -2, this will be a negative number, and this will be a negative number. And when you multiply all these three together, you will get a positive. So to the left of -2, you get positive values. Once you get past the -2, the x plus 2 switches, because you're adding numbers that are more than -2. So then this will now be a positive number. And when you multiply them all together, you will now get a negative number. And once you get past the 4, then this one switches, and so then you get a positive number. This tells us that we're going up. This tells us that we're going down. This tells us that we're going up. And so then you can see that you are going to have a relative max at x equals -2. You're going to have a relative min at x equals 4. Another way to determine whether we have a relative max or a relative min is to use the second derivative test. When derivatives are easy to find, we can use the second derivative test, and it'll be more convenient than making sign charts. So the second derivative test tells us, suppose that f is twice differentiable at the point to x naught. If f prime of x naught equals 0 and f double prime of x naught is greater than 0, then f has a relative minimum at x naught. So you can see that you have a relative minimum right here. You can see that you have a relative minimum right here. You are, your first derivative is 0, so you have a flat spot. But in that area, in that whole region right there, you're concave up. So you're looking at a curve that's concave up. Likewise, over here, we have our first derivative is 0, so we have a flat spot. But this whole time, we were concave down, so we must have been looking at that very tip. That's all this is saying. If f prime of x is equal to 0 and f double prime of x is less than 0, then f has a relative maximum at x naught. One of the downsides to the second derivative test is if your first derivative is 0 and if your second derivative is 0, then the test is inconclusive. That is, f may have a relative maximum, a relative minimum, or neither at x naught. The test fails. So here we have used the second derivative test to classify the extrema of y equals x cubed minus 3x squared minus 24. So again, what we want to do there is we want to find our derivatives. Our first derivative, we've already done this, is 3x squared minus 6x minus 24. Our second derivative is 6x minus 6. And what we want to do is evaluate our first derivative at our critical points. So our critical points were 4 and 2. So when we put in 4, we get 24 minus 6, which is 18, which is greater than 0. Therefore, my graph was concave up. Since we were looking at the flat spot, therefore, we have a relative minimum. I'm sorry, this should have been the second derivative. Y double prime of 2 y double prime of negative 2 is going to be 6 times negative 2 minus 6, which is going to be negative 18. So that tells us that our graph was concave down. Since our first derivative was 0 because it was a critical point, we were looking at the top point there, and therefore we have a relative maximum.